Hello and welcome to this session on Taming Python and DB2 for COS. My name is Jørn Thyssen. I'm from Rocket Software. I'm a product specialist in DB2 tools. So this is the agenda. I'll give you a very brief introduction to Python. What is Python? Why would you use it? Then we go into how to use Python with databases, the DB API, and then connecting to DB2 for COS, either from a distributed platform or directly from COS, which is a quite new addition. I'll show you some very simple Python program examples. Then I have a few bonus topics at the end, like how to interact with the mainframe. One thing is how do I write DB2 queries, but what about datasets, jobs, other COS services, etc. So what is Python? It's an interpreted programming language. It was first released in 1993 by a Dutch programmer, Guido van Rossum. And it's designed to be very simple. You can look up the Zen of Python. Things like beautiful is better than ugly, explicit is better than implicit, simple is better than complex, and so forth. So why would you want to use Python? There are various surveys on the internet that surveys which programming language are the most popular ones. So there's one called TIOBE. Here Python is number 3 between C and Java. There's another one called PIPL. Here it's number 1 actually. And if you look at which programming language has most job offerings open, it's Python. And also interesting, if you're a programmer, the average salary for Python jobs is actually among the highest as well. So something to consider for your next discussion with your manager if you are programming Python. In addition, it's widely taught at educational institution. That's also how I learned Python originally when I was studying at the university in the mid-1990s. I learned Python as well. So there's quite many programmers out there. If you're my age or younger, you've probably seen or programmed Python. So Python is very widely used in areas like machine learning, data science. We're also seeing it being used now in infrastructure provisioning, like IBM Ansible, which is based on Python. It's also used in scientific computing, and there's a bunch of well-known websites like Google, Instagram, Spotify, Netflix, etc. that use a Python engine as well to drive their websites. So it's quite it's used in large scale. You might ask yourself, as a system programmer, why would I use Python? And I think it's for some of the same reason that we just discussed. A lot of developers know Python, and I think if you do a survey today, a lot more developers or IT folks know Python instead of knowing regs. So if you have to write some small utility, automating some action, etc., for many people it would be much easier to do that using Python rather than regs. So that would be the reason why you would use it as a system programmer. Same would be true for DBA. I have seen a few customers that start using Python for more business applications. One area could be reporting, for instance, using the IBM DB module. Okay, so let's turn to databases. Python has what they call the DB API. Latest version is version 2. The idea is that you can have identical code to access databases across all platforms and all database vendors. So your code is more or less similar. The Python IBM DB, or just IBM_DB, is IBM implementation of the DB API version 2. So you can connect to DB2 using this module. It's maintained by the DB2 Connect development team, and it uses the ODBC drivers. The DB2 Connect team does a lot of drivers across all the open source languages. Python is one example here, but it could also be Node.js and a lot of other open source languages, so you can connect to DB2 from all of these. The source code is available on GitHub. There's also an API doc, which I've linked to both on this slide. So if you want to connect to DB2 for CUS from distributed platform, you would obviously be running Python on your LUW platform. Then you would need the IBM DB module. As mentioned, the IBM DB module uses the ODBC drivers, so you would need to have those installed, the IBM data server driver for ODBC and CLI. And then it uses DRDA to connect to DB2 for CUS. Do note that this requires that you do have a DB2 Connect license in order to be able to connect over DRDA to DB2 for CUS. When you are installing the IBM DB, is very easy. Pip install IBM DB. Pip is the Python install program, and when you do the pip install IBM DB on a distributed platform, it will actually install both the IBM DB modules as well as the required ODBC drivers. So if you don't have them already on your machine, they are downloaded and installed. If you already have them on your machine and you want to reuse that, you can set this environment variable IBM DB home as the path to your CLI drivers. Also set the lib environment variable, and then we will not download the ODBC drivers, but reuse the ones that you already have. As mentioned, you need a DB2 Connect license to connect to DB2 for CUS. If you have what's known as the Enterprise Edition, you have to obtain a license file from IBM Passport Advantage and then copy it into the license folder where the CLI driver is installed. The recommended solution is to have the unlimited Enterprise Edition and then activate the license on the CUS side with a DB2 Connect Activate program, which is part of that license activation kit. When the license is installed on the CUS side, you don't have to worry about installing a license on every client that is connecting to DB2 for CUS. If we look at now want to install IBM DB on CUS, and this is a quite new, was quite recently enhanced in early 2021. The architecture is somewhat similar. You would be running Python under Unix System Services. Again, you would be connecting to DB2 through the IBM DB, and again it goes through ODBC. The ODBC drivers for DB2 for CUS is installed with FMID JDBC C17. It's very likely it's already installed, but if you can't find the drivers, then you would have to ask your systems programmer to install that FMID. As part of that FMID, there's also a sample job, DSNAOINI which will bind the ODBC plans and packages that are required for ODBC. The default plan name is DSNACLI, so you can check your system and see if that has already been bound and is available. The connection from the ODBC driver to DB2 for CUS can either be the call attachment facility or RRSAF, Resource Recovery Services Attachment Facility, depending on your requirements. Do note that there's no DB2 Connect license required when you are connecting directly from a program running on CUS to DB2 for CUS. No license is required. So how do you install it? A minor difference to the distributed platform is that there's no pre-compiled binaries available. So you do the same pip install IBM DB, but what will happen now is that the source code is downloaded, then the C modules are compiled, and then the modules are installed into your side packages library just like normal. But the difference is here that the source is downloaded and compiled. Some important prereqs: you need either the IBM Python distribution or the Rocket Python distribution, version 3.8 or later. In addition, there's a recommended fix for DB2 version 12 and version 11. There are some Python related bug fixes for the ODBC driver that was discovered during this work. I've also included a link to more details on the actual installation and the prereqs. So obviously Python needs to be available in your path. If you're not a system programmer, you probably don't have the authority to create side packages in the default location. That's probably locked down or read-only. So one option you have here is to use a Python virtual environment. So here I show how to create such a virtual environment and then activate it. And that gives you a local place to install your Python program packages. It's also a neat way if you want to have multiple versions of the IBM DB driver installed. You can create multiple environments and have different versions installed in these environments. In addition, you need some environment variables set up. First, you need the automatic character set conversion turned on. Then there are some specific language environment run options, POSIX, and also more auto conversion. And then similar to when you're installing on distributed platform, you need to tell us where the ODBC drivers are, the macros and the headers, and so you can supply the high-level qualifier for your DB2 installation. Then you basically do a pip3 install DB. The source code will be downloaded, unzipped, compiled, and then finally installed into your side packages directory. If it goes well, it looks something like this. Some challenge that you might meet on the mainframe is that you don't have internet access. So some have restricted internet access from the ZOS system for security reasons. And in that case, you can actually download the source, then transfer it to the mainframe, and then do the install locally without being connected to the internet. At the end of this slide deck, I won't cover it today, but I have a slide with the instructions on how to do that. So you can do that. Yeah. All right. So now we have IBM DB downloaded, installed. It's ready to use. Before running a program, you need to set the STEPLIB in Unix System Services, so Python can find the ODBC drivers. You also need an ODBC INI file, and then an environment variable that points to the ODBC INI file. So see here, you do the export of STEPLIB and then the export of DSNAOINI pointing to your ODBC INI file. So here's an example of the ODBC INI file that you can use. I've included links here to the manual that describes the keywords that you can put in the ODBC INI file. You see, for instance, here the plan name, that's the default plan name. MVS attach type, I'm using the call attachment facility, auto commit, trace turned off, etc., etc. There's a lot of parameters you can set. So one important point that I've found is that the ODBC INI file has to be encoded in IBM 1047. It has to be tagged as IBM 1047, but you cannot tag it as a text file. I have a slide at the end of the deck that describes this in more detail. I'll not cover it here, but if you get some connection errors when you start Python, it's very likely that the encoding of the ODBC.INI file is incorrect. Also note that the name of the ODBC.INI file can be arbitrary, so you can call it whatever you like. Here I have the SSID and call attachment type in the file name, so I can remember what I'm using this specific file for, but it can have an arbitrary name. Alright, once the environment is set up, we'll run our first program. So this is a very, very simple program. It will fetch 10 rows out of SYSTABLES, print them, and that's it. You'll see the connect statement. We don't put anything in the parameters here. The SSID is automatically fetched out of the ODBC.INI file, so you don't have to supply the SSID. There's no user ID and password because you're running locally on the mainframe, so you're already logged on. You have a user ID and you're making a local attach, so no user ID or password. And then we have Python code. If you're familiar with Python, this looks familiar. We have this SQL statement. We call one of these API functions exec immediate, and then do a fetch, and then loop through the result set until empty, and then print the result. So if everything goes well and everything is configured correctly, you'll see an output like this, the 10 tables from SYSTABLES. Alright, so far so good. What if I want to run the same program on distributed platform? And the nice thing is that the code is the same, except for the connect. As mentioned, when you're running on COS, you're doing a local attachment, so no user ID and password is required. But when you're running on distributed platform, you have to supply user ID and password, and a connection string. So in this case, I'm just supplying the DSN name. I've already configured that connection in my DB2 driver on my laptop, so I can just point to that DSN. But there's an alternative connection string syntax where you can connect to an arbitrary system, providing the URL, the host name, port, location name, etc., as well as an alternative. But the rest of the program is similar. During one of my earlier presentations, I got the question about what about SSL if you're running distributed. Well, obviously, one solution could be just to run on COS with local attach, so no encryption is required. There's no network connection. But if you do insist on running it on distributed, you can use SSL with Python as well. You can configure an ODBC entry for the encrypted connection. Alternatively, you can use the extended connection string syntax, as I mentioned before. So here's an example of that. Database equal to the location name, you input the host name, you input the port, protocol TCP/IP, user ID and password. That's business as usual. Then you supply security equal to SSL, and then you have to supply the certificate either in form of a trust store, or in this case, I'm directly pointing to the cert file for the DB2 certificate, and then I can connect, and then the rest of the program would be exactly the same. So here the cert file is the CA certificate for the DB2 server in base 64 format. As mentioned, alternatively, you could import, if you have multiple DB2 subsystems, you might want to import those into a trust store and then point to the trust store instead for all of your DB2 subsystems. All right. So let's make it a bit more complicated. So I had this vendor program. It writes a log file in Unix system services, and I wanted to write a program to extract interesting part of that log file and then insert it into a DB2 table for doing further analytics on the output or on that data. I have an example of the log entry at the bottom of the screen. So you see there's a timestamp, there's a severity identifier, then there's a message code, some text, and then the rest is actually JSON. So the rest is a JSON document. And this is where we see the one of the benefits of Python is there's a bunch of libraries available. So there's a library available to parse JSON. So in many cases, if I'm doing this in Rex, I would probably have to write a JSON parser myself if not available. So that's one of the strong things about Python. So here's some of my program. So I make the program take parameters on the command line, including the name of the DB2 and the name of the file, and it writes something out, and then it does a connect to DB2, and then we start processing the file. So we read line by line, and then if we find, I was interested in 2 different message ID. So if I find one message ID, I call one subroutine. If I find another message ID, I call a second subroutine. So very simple code, very easy to write. So this is one of the subroutines. Python has a lot of the string processing is very easy. So if you remember back to the message, there was a timestamp initially. So I extract the timestamp, then I extract the JSON part, and then JSON loads here is just load S is a load string. So I'm basically parsing the JSON string with one line of code. That's the advantage of Python. There's a JSON library easily available. Then I build my SQL statement. I'm using a merge here instead of doing an insert and update. So I'm doing it in one statement. So I'm building the SQL statement with all my parameters I extract out of the that JSON or the line itself, and then I do an exec immediate of that SQL merge statement, and then iterate through all the lines. All right, so let's run the program. So Python, my program, the DB2 I want to connect to, then file name, the log file name from that vendor program starts processing. I've added some output so I can see progress, and it analyzed 50,000 lines from that log file and found for approximately 4,700 of the 2 types that I was interested in. So at that point, I basically declared I had won. It took me maybe 30 minutes to write this program. It worked. Everything looked good. Then I did get a bit curious what was actually happening under the covers. So I went into my SQL monitor, and I found that my merge statement was repeated 9,400 times with different literals. That's probably not good. In general, best practices is to use host variable parameters rather than literals. Also, I found that I had 18,800 commits, which is not good either. Seems very inefficient. But I did find that we were using the planned DSN CLI as expected. So back to the drawing board. I don't think my DBA will be happy with my program. So some of the things we could do to optimize it would be, how can I use host variables? And maybe I want to do a better commit strategy. And then as a stretch goal, I also had the intent to cache the prepare. Basically, I had 2 different SQL statements in my program, so there was no need to keep preparing it for each time I needed it. So I could just prepare it once and then reuse that prepare for the entirety of the program. All right, so let's look at host variables. So if you remember my big merge statement, I've basically now changed it to using host variables. For Python, the host variable marker is a question mark. Then in addition, instead of doing the exec immediate, I'm now doing a prepare. You'll see the prepare statement here. And then instead of exec immediate, I'm doing an exec of a previously prepared statement. The way that I've written my program, I'll only do the prepare once. To bind the host variables, I use the bind param API call, bind into statement 1, which is my prepared statement. Host variable number 1 was the request ID. Host variable number 2 was the username. Host variable number 3 was the timestamp, etc., etc. And then I bind all the host parameters, and then I execute the statement. So now I'm using host variables, and I'm only doing a single prepare of the statement. Turning to the commit issue. So the reason why I had so many commits was that I had auto commit yes, and there are different ways to set auto commit. You can either do that in the ODBC ini file, change auto commit 1 to auto commit 0. You can also do it in the code itself if you want to have control over it inside your code. So you can call the auto commit API call. Obviously, once you disable auto commit, you need to add explicit commits in the code. I did also find, which is probably a bit unlike COBOL or PL1 programs, that I actually had to do a commit before I disconnected. Otherwise, I would actually get an error message. So I will add some commits in the program with some frequency, and then a commit before I actually disconnect. So now I rerun my program, and in my SQL monitor, I now see the 2 merge statements from my program and being executed the expected number of times. So that looks very good. I have 53 commits instead of 19,000. So that's very good. So I think I've solved the issues, and the program actually ran significantly faster after my optimization. It was, I don't know, maybe 10-50 times faster than preparing each statement and committing twice for each statement. All right. Let's look at error handling. Again, referring back to the Zen of Python, one of the things listed there is that errors should never pass silently. So if there's an error, either connection error or SQL error, the program will actually stop, and it will show an error message and stop. So it's unlike COBOL programs where you can do an exec SQL, and unless you write your own logic afterwards to capture or intercept the SQL codes, then the program will just continue no matter what happened in that SQL statement. So Python is different here. You can of course intercept the error messages, the errors, if you want to have special handling for that. So it has a try, except, else. So one example would be here, like try, prepare, and then prepare failed, and you show the error message, and then you have some error handling in the program. Of course, if you just want to have the program terminate, then you don't need to intercept that error. There are a few interesting API calls in this area. There's connection error messages, there's statement error and statement error messages. The statement error is your SQL state, and the statement error message is the SQL CA as a formatted string. So we have one example below here that I have a SQL statement with some problem in it, and you get an SQL code -440, and you get the string out similar to what you're used to. I have included a link at the bottom to the manual that describes these API calls and error handling for the DB2 Connect, for the IBM DB module. All right, let's look at another use case, which is calling stored procedure. So DB2 has a number of interesting procedures supplied with DB2. We'll look at several of these here. So the first one is DSNUTILU or DSNUTILV for executing a utility. So for calling a stored procedure, IBM DB has a call proc, and then it has fetch as SOC and next result for fetching rows from a result set and then iterating over result sets. Some stored procedures return multiple result sets, and so you have to iterate through those if you need them. So here's some sample code. The first part here are my parameters to DSNUTILU, the utility ID, restart, yes, no, the actual utility statement. So we see here we have a template statement, then somewhere inside, where is it? Oh, here we have the REORG statement, and the return code. The way you call a stored procedure in Python is to call the call proc with the connection identifier, the name of the stored procedure, and then a vector with the parameters. And then if you want to capture the output, you have an assignment where you capture the output. So the first parameter returned is a statement identifier. That's the one you're going to need for iterating over the result sets. And then you have the parameters listed that you want to capture as well. And then I loop over the result sets. So as long as statement 1 is not null, I fetch rows, and then I loop over all the rows of that result set, and then I go to the next result set once I've done fetching, so you can iterate through all the result sets. So if we execute this program, run my program, it calls the stored procedure, and then in my case I print out the first result set returned by DSNUTILU is the utility output. So basically I'm returning the utility output and printing it to the screen. So relatively simple, very few lines of code for calling a stored procedure. Another DB2 supplied stored procedure is the admin command DB2. There's also an admin command DSN to run bind commands. But here I'm using admin command DB2. I've written a program that's very similar to the one I use for DSNUTILU. Pass the command on the command line. It calls admin command DB2, and admin command DB2 returns the command output as the first result set, and you can actually pass some special parameters to admin command DB2 to say that, for instance, I'm doing a display buffer pool and I want to have the output returned in a tabular format. Then admin command DB2 will actually return the output from display buffer pool in a tabular format that is easily usable for other purposes. Otherwise, you would have to pass the output of that command. Then a few months ago, I saw a post on the IDUG-Db2 mailing list. The topic was about upgrading explain tables after you've upgraded DB2. Usually, the explain tables change with each release of DB2, and so you have to upgrade those. And if you don't upgrade them, you'll typically get like a plus SQL code from the bind or explain that your explain tables are not up to date, or it might even fail in some cases. DB2 does ship a stored procedure, admin explain mains, that can create new explain tables, upgrade existing ones, create aliases, etc., etc. It has a bunch of options for maintaining your stored your explain tables. So the challenge is that it's a stored procedure, so it's you need a program to call it essentially. So I wrote a small Python program to upgrade plant tables, calling the stored procedure. In this case, I basically did a loop through trying to identify all plan table sets on my DB2 subsystem. That there might be, if users have personal tables, there might be hundreds or thousands of sets of tables, and then I just iterate through them. For each schema where I found a set of plan tables, I call the store procedure to upgrade them. So in this particular run, I'm using the preview mode, so I'm actually not doing anything. Then I'm doing the action standardize and create, and then table set all, so creating a new one. There's also upgrade options, etc., etc. So you can easily write a program that loops through and then upgrade all your plan tables in a single easy program. That can be very useful. As mentioned earlier, one of the advantages of Python is all the libraries that are available. There are literally thousands of libraries available for Python for all kinds of tasks. So in the second example, we saw the use of the JSON parser. IBM DB is also a module or library. Some of the libraries like IBM DB is a bit special because they are based on C code and have to be compiled. So while most of the libraries listed here will work on all platforms, there are a few libraries that have to be ported to Unix system services, and IBM DB was one of them, but there are a few others out there as well. So some of the interesting libraries that I have on my personal list is obviously IBM DB, the whole topic of this presentation. Another one is requests. This is for making REST calls, and we will see that in an example in a moment. There's Flask. That's a library for making web apps, so you can easily make a web app on your using Python. For instance, you could make a web app or REST APIs based on Python that offer services on your mainframe system. So, for instance, the upgrade of the plan table I just showed, you could make a small Flask application that serves that as a REST API. So a developer in a pipeline, they could call and get the explain tables created. Some other interesting libraries: Jupyter, Pandas, Matplotlib for analytics, and I have an example of that as well. There are Python libraries for creating PowerPoint presentations and Excel spreadsheets. This PowerPoint presentation was created by hand, but you can actually create PowerPoints from Python. Internally in Rocket Software, some of our product managers, they actually created a small Python program that runs a Jira report, extracts the product roadmap, puts it into a nicely formatted PowerPoint, so you don't have to maintain this PowerPoint presentation. You can just run your Python program, once a week, and you have a fully updated product roadmap. So there are some very nice use cases for that. The Excel module, maybe you could combine that with the IBM DB, so you're running some kind of report against DB2 for COS, extracting the data and formatting it into a spreadsheet available for download. Maybe you also use Flask to make this available as a web app, so you just go onto a web app and you can download an Excel spreadsheet with the output from a query. There's some nice, a lot of things can be done this way. All right, so let's install Jupyter. I'm using Conda to install Jupyter here. Rocket Software makes a large number of open source tools available on a Conda channel. I won't go into the details of Conda here, but you would need to download Mini Conda from Rocket Software, and then you can download additional open source software for COS from that Conda channel. So here I create an environment, then I add notebook, the Jupyter notebooks, PIP, XLC wrapper, Thyssen, Panda, Matplotlib to that environment. I activate the environment, and then I install IBM DB into that environment, so I have it available as well. I run the Jupyter notebook generate config, So it generates a config file for Jupyter. I edited the config in my case. I added my own SSL certificate so I can have a trusted encrypted connection, and I changed the port number for the Jupyter server. Then I created a directory for the notebooks, and then I launched Jupyter Notebook. You will see something like you have on the bottom of the screen here, servers up and running, listening on port 8888, and this is the URL for connecting. Then I launched launched that URL in my web browser. I did install the DB2 IPINB module. That module is available on GitHub. There's a link at the lower right of the screen. That Jupyter module adds various shortcuts for DB2 connectivity. So you could in the Jupyter notebook you could write code just like I showed you earlier for the Python programs, where you do a connect and then you do a exec and then you loop through the result set, put that into a panda frame, etc. But you quickly get tired of that. With the extension module, you can write things like this. So you just run the module, you do a %SQL connect to my DB2 subsystem, successful, and I do a %SQL select. I select some variables, run a query, shows the output very nice in a table. I can also do graphing. So here I'm doing %SQL, doing a graph, select DB name, count from sys tables, etc. So I show the databases with most tables on my system. So easy to do all kinds of analytics with Jupyter. And as you can see, this runs on COS as well. Okay, so the final topic of today's presentation is interacting with COS. Now we've seen how to interact with DB2 for COS, but if you're running on the mainframe, you may want to do other things on the mainframe. If you're a system programmer, you might want to interact with data sets, submit jobs, and potentially interact with other COS services. Unfortunately, there's not really any de facto standard library for COS for Python, and there's very little native support for interacting with the mainframe. But there are a few modules that are available. So there's the OS module, which basically runs a command in a shell. You can do things like this. So you can run uname and then read the output from running uname and check for things from that output. You can also run TSO commands this way. So again, there's a USS command called TSO CMD, which allows you to run TSO command. So I can allocate a data set just by calling TSO CMD, execute the command and retrieve the output. So there are different ways of running USS commands. If you're looking at data sets, if you have the Rocket Python, it supports the reading from MVS data sets by using the the normal / syntax for referencing MVS datasets from USS. So here I can open a sequential dataset. Rocket Python also has a ZOS module with Dynalog, the ability to load a module, and PS for checking the processes. IBM also has IBM C open automation utilities. They are free of charge, can be downloaded. They wrap MVS utilities like IDCAMS, IAB copy, etc. It also wraps the SDSF Rex API, and they supply shell scripts that call these utilities, as well as Java and Python APIs. So if you're creating some, if you're a system programmer creating a program for, automating some action or some productivity enhancement program, then I think this is some nice modules that gives you an easy way to access certain MVS utilities and SDSF, etc. However, if you don't write a high performance batch program because it is somewhat inefficient to do an IDCAMS list cat just to check if a dataset exists. You can also do a lot of stuff with the ZOSMF REST APIs. So they are REST APIs for datasets, for jobs, operator commands, and many other things. So this is where the requests module, Python module, comes into play. So I import requests, then I have my URL, which is one of the REST APIs from ZOSMF, and I basically do a get against this URL. So you'll see I'm calling the REST jobs API, so that's SDSF, prefix something, owner asterisk, so it's essentially equivalent to going into SDSF and doing a IZPS asterisk and filter owner asterisk. And then I do a get to that URL, and then I retrieve the response, and I get back the response, and I can print out the result. So if you run this Python program, you'll see something like this. So it's a Python equivalent of SDSF. The nice thing about this Python code is that it will actually also work if you run this program distributed, because it's connecting to ZOSMF over the network leveraging the REST APIs. But obviously it's also expensive to call a REST API. So again, you can use this for automating tasks or productivity improvement programs, but probably not useful for a high performance batch program. Then finally, there is something called CFFI, which is a way to create a Python wrapper over C libraries. So instead of doing the IDCAMS list cat to check if a dataset exists, you can call the access C routine, and then you could wrap that in the CFFI to make a Python library available that gives you the access C routine access to that C routine. That is obviously much more efficient and high performant than some of the other options, but you would have to use the CSFI module to generate that wrapper over the C library, so it's not a standard solution. So that brings me to the conclusion. So I hope you learned that Python is very popular. Python can talk to DB2 for COS. That has been the case for a long time. But what is new, or relatively new, is that you can also, obviously you can run Python on COS, and that has been available also for some time. But the new thing is that you can now run Python on COS and also talk natively to DB2 for COS. So that's it. Thank you very much.